Hi everyone, let's talk about homework 6. In this homework, we will continue doing the hypothesis test for population mean, but instead of t-test, we are going to focus on something called sign test, which is a procedure that we are supposed to use when we don't have large enough sample. And on the other hand, we will also talk about how to deal with population proportion inference, which is the P thing. Like I said, there are 4 different categories when we are looking at this problem, depending on how many groups you have and how many categories you have. But the bottom line is, regardless of the number of categories and groups, you can always use chi-square test. But the thing is, the chi-square test is approximation, which means in some of the scenario, it's not working the best. For instance, when you have a 2x2 contingency table, although you can still use a chi-square test, but for that certain scenario, your best bet is to do Fisher's exact test. And similarly, when you have only one group and there are only 2 categories, the best bet is binomial test as opposed to chi-square test. So without further ado, let's take a look. The first question is about the two-sample t-test, and more importantly, it is paired two-sample t-test because we collect the MCPP measure and the placebo measure from the same individual, and by doing so, we can eliminate the individual variability. I have typed in the 2 groups of data and also calculated the mean of each of the group in order to verify that we have typed in the data accurately. And the next thing that I want to do is to do the t-dot test in order to get the t-statistic. The first group is MCPP, the second group is placebo. And don't forget, we have to specify the paired option equal to true. We get the t-statistic, which is 4.17, and that solves part A of the question. And in part B, the null hypothesis is obviously MCPP has no effect on the weight loss, or in other words, mu1 equal to mu2. Remember, we always set the equal sign in terms of the null hypothesis. In the alternative, it's supposed to be MCPP has some effect on the weight loss, but the context does not specify which side we should go to, so we can just keep it vague. The part 3 is the p-value based on the t-statistic. It's 0.003, and that is smaller than alpha level, so we have to reject the null hypothesis, which means we have significant evidence to show that MCPP has some effect on the weight loss. The idea of the second question is almost identical to the first one, except for you are asked for a confidence interval, not a hypothesis test. And I have all the data here, the treated group and the control group. I have also specified the paired equal to true because obviously this is a parity test, and I have also specified the confidence level equal to 0.95, which is kind of redundant because, by default, R will set the confidence level equal to 0.95. I'm just specifying this explicitly to emphasize this point. As long as we run these 3 lines of code, we'll get a confidence interval that is from negative 0.5 to positive 0.7355 something. So that is 95 confidence interval for this paired t-test. In the second part, you're supposed to do this the wrong way by treating this as a independent two-sample t-test. This option you change paired into false. Or even better, you can just remove this option because by default, R will set paired to false. If you run this line of code, you will get a different confidence interval from negative 0.8 to positive 1.05 something. This confidence interval is much wider because in this case, which is two-sample t-test, we have to account for individual variability, and that necessarily inflates the confidence interval. In question 3, we are supposed to use sign test, but before we actually do that, I'd like to review a little bit about the idea of sign test. We are supposed to use the sign test in a scenario which is pretty much similar to the parity test. We have a before group and we have after group, and we are really interested in figuring out whether there is a difference among these 2 groups. And obviously the null hypothesis is there is no difference among these 2 groups whatsoever. So if that's the case, the third column, which is like the different column, should be kind of fluctuating around 0. So in order to check whether or not the null hypothesis is true, we're supposed to use a sign test. And what actually happens underneath the hood is a binomial distribution, because if you think about it, all the observations should have 50% of chance to go up above 0, and the other half should be go below 0. So that makes p equal to 0.5, and that is why we actually have to use a binomial distribution underneath the hood, and that's why the name of the test in R is actually called binom.test. Okay, you might wonder why we are talking about this. Actually, it's because in this case, in order to make this sign test work, you have to understand what is going on, because the syntax is not as foolproof as t-test is. I have the two groups of data, and I have also constructed a third variable, which is the difference, which is given by the treatment group minus the placebo group. As you can see here, some of the observations being negative and some of them being positive and the other being 0. But mind you, the negative here means successes, because we are talking about the seizures that the patients are having. So a smaller number means a better effect of the drug. Actually, this is success, and this is actually a failure. Well, next question you might ask is, well, what is the total number of observations? Because it is an essential element to know what is the total count of trials. So that can be found by the length function, and we have 20 trials in total. And next question is how many successes we got. One way to do this is just count this manually, just count all the negative numbers that you got. And a smarter way is to do this. Difference smaller than 0. You are actually returned with a series of booleans. And the true means actually indeed this value is smaller than 0. We can actually sum up these booleans, and we got 14 in this case, and 14 means we have actually 14 of these members being true. Well, it looks like we kind of figured out everything, but not quite yet, because first of all we have to deal with the tie here. The typical way to deal with the tie in a sign test is to pretend that they don't exist, and that is why we have typed in 19 here as opposed to 20, because there is a tie in the last position. We only have 19 observations. We pretend that the tied value doesn't exist. And the second thing we have to pay attention to is a directional test. We have specified alternative as greater, because our alternative is to show that our drug is really working, and we want to see more successful cases, and that is why the alternative is specified as greater. This question is about doing inference of population proportion, which is that p parameter. Actually, we have two different ways of doing this. One of them is based on the binomial test, which is the exact method, and the other way that we can do is based on central limit theorem, which is to assume that p hat has to follow a normal distribution when the sample size is large. So you can use either way of them, and I'm going to present both of them. So first of all, what you can do is binom.test. Again, this is the exact method. You are supposed to specify how many successes you observe, which is 28 in this case, out of 580. You are going to get a 95% confidence interval, which is from 0.03 something to 0.069. A second way that we can do this is based on that central limit theorem thing. You can just type in prop.test, and still the number of successes, in this case 28, and the number of total counts, which is 580. So if you run this line of code, you will get a little different confidence interval, which is from 0.03 to 0.069 something. They are like slightly a little different, but pretty much the same. So you can use either one of these. This one is pretty much similar with the one before. You have to calculate the confidence interval based on the sample proportion data, and again, you have two ways to deal with this kind of problem. One is exact, the other is based on approximation and central limit theorem. As additional part of the question, you have to give interpretation of what this means when you have a confidence interval. We got 69 of the infants who have adverse reaction thing, and the total count is 339. So that is how we specify this model. This is the exact method, and this is a method based on the approximation. And I do recommend you to use this method because this is exact result. So we run both of these lines of code. As you can see, the exact binomial test gives you the 95 confidence interval from 0.16 to 0.25, and the approximation also give you something similar from 0.162 something to 0.25. So again, you can use either of which, but I recommend the first one. Part B is nothing but an interpretation of your confidence interval. You can say we are 95 confident that the probability of adverse reaction in infants who receive their first injection of vaccine is between 0.16 to 0.25. This question is exactly the same with the previous two questions. As we talked about, you only have to specify the number of successes being 14 and the total counts being 71 in the function of binom.test. So I'm gonna trust you guys with this. Okay, this one is about chi-square test. And in this scenario, we only have one group, but we have three categories. That is why we have to use chi-square test, because the category is more than 2. The basic format of chi-square test is usually what you expect versus what you really see. You are supposed to use a format like this. Chi-square test is the function name, and counts is something that you really have observed. In this case, is like 155 being white and 40 being yellow and 10 being green, something like that, the reality. And the probability here is the second vector, which is what you are expecting to happen, or in other words, what happens in your null hypothesis. I'm calling this the probability for a reason, because whatever vector you are passing in here, it has to sum up to 1. So let's see how to work on this problem. Okay, so in order to do this, we use the chi-square test as the function. The first argument we are supposed to pass in is, the real value that we actually have observed. The second argument is the probability that we want to pass in, which is our speculation or whatever the null hypothesis is. But in this case, we're not lucky because we are given something like a ratio which is 12 over 3 over 1, and that is not a probability. We have actually convert this into probability. So one thing to do is we have to sum this up, which is 12 plus 3 plus 1, that is actually 16. So we have to convert this ratio into probability and put it in here. 12 over 16, that's the first probability. 3 over 16, that is the second probability, and 1 over 16 being the third probability. By running this line of code, we can get the final result, which is chi-squared statistic being 0.69106, and the p-value is even bigger than any threshold that we can think of, so we fail to reject the null hypothesis. This one is pretty interesting because if you actually look at this description of this question, there are only like 2 categories, which means we definitely have better solution than using a chi-square test. Like we can use binomial test, which can yield much better results. But since the textbook wants us to, fit in the framework of chi-square test, so let's do this. In order to fit in a chi-square test framework, we have to still find out what we expect and what we actually see. The thing that we see is 216 successes out of, 933 trials. But the tricky thing is the expected value or our null hypothesis is not given explicitly. But one thing from the textbook is the random timing of the birth. Think about this, we have 7 days in a week. So if it is totally random, every single day would have a chance that is equally the same, which is 1 over 7. So the probability of seeing someone born on a weekend should be 2 over 7 because we have 2 days on a weekend. Probability of someone born on a weekday is actually 5 over 7. The function we're using here is still the chi-square test. The first argument, as usual, we have to pass in the real value that we have observed. The first category is the number of successes, and the second category is the number of failures. And the second argument that we are passing in is the speculated probability of each of the category. The first category is obviously the weakened category 2 over 7 if it is distributed randomly, obviously. And the second one is like 5 over 7, which is the probability of someone born on weekdays. So after we got everything here, we can run the code and get the following result. And the chi-square here is 13.3, and that answers part A of this question. Part B of the question is about the null hypothesis and the alternative. So in the context of this question, actually the null hypothesis means the timing of birth is actually random, and the alternative is obviously the timing of birth is not random. And part C, the p-value here is, it's almost like 0, and because it's smaller than alpha, which is 0.05, so we can reject the null hypothesis, which is saying that the timing of birth is actually not random.